Okay. So, no. Um, and welcome everybody. Today I might to complete some issues on structure dynamics for elasticity and start with the content about uncompressible and steady flow. Well, first of all, I want to share my presentation, and I want to start on the recording I have in mind to recover our last lectures in the first week. In particular, we have two lectures of about 2 hours and one lecture of 1 hour only. And I would like to recover this lesson next week. In the typically you have less lectures in the afternoon, so it could be a good idea to have our lecture in late in the morning, and Tuesday could be a good day for me. So could be Tuesday, not the day after tomorrow, but the other Tuesday after 10 days. And so my idea is to recover on Tuesday, in particular Tuesday the 28th, for example. And yes, okay. Wednesday, excuse me, not Tuesday, Wednesday on the 28th. And so Wednesday, I write this on the chat. Recover. Let's lecture on Wednesday the 28th. Question: if anybody at 11:30, for example, and this is the idea. Of course, this recovery lesson are all on remote way. Okay, so only distance, not in present. Okay. So this is not okay. Change. Tutta la mattina ce la Frequent, mi pare.
Alle 11 alle 14.
Ah, ok. No. Correction. On 9 or 8 if you want. 8 is okay by me. 8, 10. Okay. However, I will confirm this point. Okay. Start the recording and then go. So okay, so we concluded that the answer, the response, the time response in model coordinate is given by this equation here. And model coordinate, we have this. And so we have to go back to the original coordinate. But first, we have to rewrite this equation in vectorial, in vector notation. We have that the vector of the model coordinate is equal to, we have omega to the -1, which is this diagonal, and we have a sign matrix applied to the initial condition on velocity. So I have just translated this part here. Then I have another initial condition term like this, and so we have this, For this part, we have a cosine matrix plus a cosine matrix as a function of t on the initial condition on the model displacement. And finally, we have this integral, which is plus omega minus 1 integral from 0 to t. And here we have this omega to the power minus 1. Okay, I've already written, excuse me. So I have this sign matrix, but in a convolution term like t minus tau as applied to E vector, model vector, tau in the tau. Okay? So I've simply rewritten this in a vector notation. And therefore, we have a part associated to initial condition, and this is a part related to the forcing term. I emphasized last time that we don't have this forcing term in elasticity. We typically have something related to the state as well. However, going back to the original coordinate, we have that the original coordinate displacement is equal to zeta matrix by the modal coordinate, and this is true in any time, but is also true for the initial condition. So this is also true for q0 equal to zeta q bar 0, and also for the velocity q bar 0 equal to zeta q bar. Excuse me, this is model, this is model, this is model. Okay? Okay, so anytime the solution is equal by zeta by this. And so we have omega to the minus 1. We have the time sign matrix applied to q dot, which is this here. And so we have to invert this zeta matrix. And here there is a point to be underlined. The eigenvector matrix, the structural eigenvector matrix zeta, is not a standard orthogonal matrix. Is an orthogonal matrix, but with respect to mass stiffness. Okay. Therefore, we have to consider the inverse of this matrix for having this term or for having this term here as a function of the other. We have to take the inverse because this is not true. The following zeta transpose is not equal to zeta to the minus 1. In fact, the orthogonality is the following. We have that zeta transpose m zeta is equal to, for example, the generalized diagonal mass matrix. This is true, but this is not. And so if you want to use this, if you pre-multiply this by m bar to the minus 1, m bar to the minus 1 by zeta transpose m, zeta equal to the identity. And so by this relationship, one can easily realize that ta-da, this is the inverse of the model matrix. in that we have that all this 3 multiplied by zeta is the identity. So the inverse is unique. However, this is the path for having free the inverse of the model matrix without inverting anything. And this path is mandatory because the orthogonality is not a standard orthogonality. So for this, we have to use this. We may use this, okay? And again, the other term, we have this, so plus cosine. Q bar is again zeta minus 1, and again we have this applied to this initial condition, and finally plus the forcing term, the integral is minus 1 applied to this convolution integral on the sign matrix, and instead of this E bar here and only here we have zeta transposed on applied to E vector, which is the original input vector, to be convoluted in as tau function in d tau, and that's all. And this is the final formula giving you the dynamic response of your forced problem as function of the initial condition and the forcing term. Okay? And as you can see, the generalized dynamic problem, the original dynamic problem, which was this, is here solved in a closed form by the knowledge of the eigenvector and the eigenvalues. Oh my God. The eigenvector and the eigenvalues of the matrix N and K. This is the solution. So you have the solution of the second order differential equation in a closed way. And this is in time domain, but you could also consider this time domain solution for finding the Laplace domain solution. The Laplace domain solution means that you want to know the output in terms of the Laplace transform of your output as function of, as given by this input. Okay? And you want this equation by introducing a transfer function matrix such that multiplied to the input is able to give you the output. And the interesting thing is that the eigenvector-based solution here is able to give you the transfer function matrix in terms of the eigenvector of the problem. You have just to take the Laplace transform of this. And if you do this in the case of, for example, of 0 initial condition, so Q0 equal to Q dot 0 equal to 0, and take the Laplace transform of equation y. This is the equation y. You have the following. You have q bar tilde equal to, we have zeta here, so zeta. By here you don't have this term, and you don't have this term because this term are neglected now for zero initial condition, and so we have only this here. And look that the time dependency is only in the sign here and in this e, which is a function of tau. So you have a convolution of two functions. You have many convolution products because you have to multiply a matrix, okay? But each term is a convolution integral. And this convolution integral, the Laplace transform of this convolution integral is simply the product for the famous Borel theorem, is the product of the single Laplace transform of the factor and the product. And therefore, when you Laplace transform the sine function, you have I forget something. Look, this is my experience. Yes, I forget this denominator. Forgot. In fact, here is the term. Here is the term, and so and here I have the Laplace transform of this is the sine divided omega n, but this here is m n. Okay, multiply. So I'm sorry for this, and so I have this model mass to the -1. Model mass to the is a diagonal matrix, so the order of the multiplication is uninfluenced. Okay, and excuse me for this. And so when I take the Laplace transform, I have that the Laplace transform of the sine is, remember, the Laplace transform of sine omega t is equal to omega by 1 plus s square plus omega square. And so here I have sine divided by omega, and this cancels this other omega -1 here. So at the end of the story, I have a diagonal matrix composed by the Laplace transform of the sine. So I have 1 on s square plus omega square n. But I have also a generalized mass here as a product of these two matrices, this and this. Then I have this transposed, and finally the E tilde S. So this is the final relationship relating the output with the input. And so we have Q bar tilde equal to H S on E tilde. And therefore, this is the H matrix, the transfer function matrix. this quantity here. And this represents the fact that the transfer function matrix is something related with the eigenvector and the eigenvalues, of course, of our problem. But we can realize this in this vision, but in the other vision, we can evaluate this matrix directly, taking the Laplace transform not on the solution, but on the original differential equation. If you take this Laplace transform on the original differential equation, if you starting on this, again with 0 initial condition, one has s squared m plus k applied to q tilde equal to e tilde. And therefore, in order to have this form, we have to invert all this matrix. And we have that h s is equal to s squared m plus k to the minus 1. And this represents the fact that the transfer function matrix can be identically represented only or in this way as a function of the mass and stiffness matrix, or in this way as a function of the eigenvector and the eigenvalues of the problem. Okay, this is identical. A final comment of this point is the vision not of the Laplace Fourier vision, but the Laplace domain vision, but the Fourier domain vision. And if you consider this limit case of S going to j omega, remember that S in general has a real part and an imaginary part. If we consider this limit in the complex plane, this means that you are not considering the h function as a function of complex variable with s equal to r to the real part of s, which is alpha here, and here the imaginary part. But you are considering the restriction of your transfer function on the imaginary axis. So this is the vision of frequency response function vision in this domain here for S restricted to j omega. And if you do that, the h omega is equal to zeta 1 on, instead of s squared, you have minus omega squared plus omega n squared by zeta transpose. Note that these are constant and these are current variables. Omega is a current variable. Omega n is a value, as a real positive number, omega n squared. And here you can find the concept of resonance. But for visiting the concept of resonance, you have to use, you have to interpret this h of omega function in a proper way. in particular, you have to consider I don't want to consider these issues because it's very standard. It's just a recall for all of you. The concept of resonance is not an instability of the system, but is an issue concerning a forced response of the system to a steady harmonic input. Okay? If you want to be, if you don't want to pass my examiner elasticity, you can simply say to me that the resonance is an instability phenomenon, is an instability of the system. The responsible of the resonance condition is the input, which is able to throw a suitable harmonic motion to provide energy to the system as direct channel. When the frequency of the input is equal to an internal frequency of the system, a door is open to the system, to the input of the system. And then the input is free to provide energy to the system, up to the system grow and up to the collapse. But the system itself is not unstable for this. The system is stable. Okay? It's just a question of tuning, lovable tuning, love question between input and system. Feeling question between input and system. If you want to interpret this in a systemistic way, you are taking the input as to be an independent oscillator itself, an harmonic force, and you're putting this independent oscillator inside the system as another close to a system independent oscillator, and then you have a double pole. And with a double pole, this is another way to see, interesting way to interpret mathematically this issue. But this is not, for the system alone is stable, because originally the system has only one pole, not double. The resonance is something like the possibility to have a double pole for the system, taken by the input. Okay? Okay. So the concept of resonance is when you have this omega close to this omega. But honestly, one could say, why I have to take this omega close to the other omega? The answer to this honest question is the following, because you can interpret your frequency response function in a steady motion, and in a steady motion, a steady harmonic motion with for example, EI in time equal to 1 sine omega t. So look, this is a time function, absolutely time function, but harmonic with a unitary or unit amplitude, 1 Newton, pushing harmonically. One can obtain in steady motion the following, that the output in another degree of freedom, J, steady motion, is equal to the amplitude, the complex amplitude of HJI evaluated at the frequency omega by the sine of omega t plus the phase of this number ij. Okay? This concept is a standard concept in structural dynamics, and therefore, if you have that HJI as a function of omega is a function of omega of this type, and this is exactly of this type, as you can see here. As you can see here, because you can rewrite this in component, not in absolute matrix notation, but in component. This can be written in this way. Excuse me, zeta R ij, excuse me, R I, I R J divided by omega square minus omega square R. So this is identical to this, and therefore you have exactly this sum of this term here, which is something like 1 on omega square minus omega 1 to the power 1, if this is omega 1. This is the second mode of vibration. This is the third natural frequency omega 3, and this is the fraction corresponding to the fraction 1 on omega square minus omega 2 square, and this is corresponding to 1 on omega square minus omega 3 to the power 2. And therefore, when you are exciting in this frequency with omega, capital omega, close, for example, to omega 1, you are here, and here you have a singular point going to infinite, and this means that your steady solution is exploding. But remember the story of the couple pole, the double pole. You are exploding in steady solution because your solution is a solution of this time. Type of t by sine omega t, where you have a couple, where you have a resonance condition. Your solution in time of this type. So the steady solution is infinite. Okay? And this does not have any common concept with instability. It's not an instability. It's a resonance. Okay? So after this, my comment is the following. We have studied this system. In Laplace domain. And this is a forcing term. When we want to study the aeroelastic analysis, the external force on a wing are physically given by a pressure distribution. This is the normal, and we have a pressure here. And so the force per unit surface are equal to minus pressure by N everywhere. A distribution. Okay? This is the physical aerodynamic force. A is for aerodynamic. A is aerodynamic. The pressure is given by somebody. Now, here you want to put a load. And this load here, remember, is the component En is equal to the projection on the body surface of your load, which is T. I write minus P aerodynamic by N dot projection to the psi N shape function. Okay, look, if we are using model coordinate, we have just to change from this to this model, or you have to introduce the model shape function bar, the mth shape function as equal to a combination of the component of the mth eigenvector with the finite element or hat function, and this hat function are psi function. So when you use our model coordinate, you have in mind consistently all this Lagrangian quantity of this shape function, and we underlined the concept that the point of view is identical. So if you want to write your Lagrange equation of motion in model coordinate by the aerodynamic load, you have to write S square, excuse me, this is S square, not S, of course. In Laplace domain, you have S square, the modal mass matrix, modal mass matrix, the modal stiffness matrix, and here the modal coordinate in Laplace domain, equal to the modal generalized force. But the modal generalized force here, what is the projection of the shift, the pressure distribution. I am considering the aerodynamic load, the pressure distribution as force per unit volume, and viscous flow, so only normal component of the pressure. Pressure distribution, another typical confusion and error of the student, pressure distribution is this quantity also in unsteady flow. Pressure is the pressure, steady and steady. Okay, so pressure distribution dot, look, modal shape function consistently. So M, you have to project to the M modal shape function, ds. Okay? Now the point is, okay, in the aeroelastic case, this keep to be valid, keep on being valid, okay, as well. But what is the point? The pressure distribution is the pressure distribution as given by the motion of the structure. So you have to consider unsteady boundary condition for evaluating your pressure distribution. So in the elastic modeling, time is it? Okay. So in the elastic modeling, we have, excuse me, I have to add a sheet here. In the elastic modeling, we have to close this loop in this way. S square m bar plus, consider the generic m equation, excuse me, consider, to be clear, in the aeroelastic loop in modal coordinate, we have the equation of the structure. We have as output the modal coordinate, each modal coordinate. We have the aerodynamic. We have to impose the unsteady motion as given by the modal coordinate in the aerodynamic, and then evaluate the generalized aerodynamic force as input of your system. And this closed loop system is our aeroelastic system. If you consider here a really external load, you have this. But practically in this kind of concept, we have here, for the equation, we have the generalized mass as applied to S square plus the generalized stiffness, okay? These two are multiplied by Q bar M tilde equal to E M, but attention, it is my intention to express this quantity as a function of Q bar tilde. Is it possible to expand this dependency? Yes, it is possible, because this EM, what is this? Is the projection on the surface of the pressure distribution, which is a function of something, aerodynamic pressure distribution, and dot psi m ds. The pressure distribution depends on what? Boundary condition. And the boundary condition on the wall may be steady or unsteady if the wing is moving. But remember, the motion is unknown of your problem. So if you are able to express here the boundary, the wall boundary condition on the wing wall, as input for your aerodynamic package, at the end of this operation, in a linear field, you may hope to have something like a matrix applied to the motion of your body. And what is the motion of your body? It's represented by Q bar. So the openness of this process is to succeed in express this analytic relationship, translate this analytic space continuous analytic expression in algebraic, in this algebraic discretized representation here, but with this ES as a metric depending on S in general. Okay? And if this F is our really forced term, this forced term should be here. But after this inclusive operation, include the aerodynamic inside the system, what you have? You have at the end something like m s squared plus k m minus, indeed, as any kind of aerodynamic operator, the aerodynamic operator has a gain constant, which is the dynamic pressure. When you have an aerodynamic force of any kind, you have dynamic pressure by blah, 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 CL in steady motion. So indeed, here we will try to put in evidence a dynamic pressure QD. QD is 1/2 rho u to the power 2, the dynamic pressure. And so we have dynamic pressure EM on, excuse me, EMN. And I want to stress the fact that this term is diagonal, this is not. I have a matrix here, a full matrix here, and I have a diagonal matrix here in the right hand side. So to be consistent, I have to insert here a Kronecker delta, NM, Kronecker delta NM, and then summation on Q bar N, summation on M equal to Fn. Excuse me, here I have blah, 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 M. Okay? Okay. And so this matrix is diagonal, this matrix is diagonal, this matrix is not diagonal. And it's the aerodynamic matrix. So my ambition is to have a general theory for expressing this force. It's possible to have a general theory for identifying this aerodynamic matrix for potential flow. Yes, it is possible. And we will build this operator from now on. Okay? Okay, so I am finished this hour, this introductory hour. We have closed the structural dynamic part, and then we are ready for talking about aerodynamic, unsteady aerodynamic flow, some recall on thermodynamics of flow, and the unsteady aerodynamic issues. And the unsteady aerodynamic issues for potential flow are focused on the mechanism of vorticity for contact surface in fluid aerodynamic. So contact surface discontinuity, which is the second kind of discontinuity beside the shock wave discontinuity. The shock wave discontinuity is a discontinuity in the normal component of the velocity. The contact discontinuity is a discontinuity in terms of tangential component of the velocity. The kinematic of the contact discontinuity is the key kinematic, is the key unsteady effect for the steadiness of potential flow. For going beyond and cross the problem of the D'Alembert paradox. Okay, for generating lift, for generating unsteady lift. And this is the point of the next lectures. Thank you, and see you tomorrow. Tomorrow, no, the day after tomorrow. And we have in mind to